transformer inrush current is a phenomenon that occurs when a transformer is initially energized. This inrush current can be significantly higher than the transformer's normal operating current. It is important to understand inrush current to properly size overcurrent protection devices, or OCPs, such as circuit breakers or fuses, to prevent nuisance tripping. The magnitude and duration of the inrush current depend on several factors, including the transformer size, impedance, core material, and the point on the voltage waveform at which the transformer is energized. When a transformer is energized, the core's magnetic flux lags behind the applied voltage by 90 degrees. If the voltage is applied at or near its zero crossing, the core flux will need to reach its maximum value in 1/2 cycle. This rapid change in flux requires a large magnetizing current, resulting in the inrush current. The inrush current waveform typically decays over several cycles. The first cycle has the highest peak. Subsequent cycles see a rapid decrease in peak current. The duration of the inrush current event can range from a few milliseconds to several seconds. The provided data shows the typical calculated inrush current for a 30 kV ampere, 480 volts to 208 volts by 120 volts, three-phase transformer. Let's analyze the data. The peak inrush current during the first cycle is 460.66 amps. This is the highest instantaneous current the overcurrent protection device will experience. The average inrush current varies over the first 10 cycles. The average for the first cycle is 134.93 amps. The average current decreases as more cycles are considered. For example, the average from cycle 1 through 2 is 103.61 amps, and from cycle 1 through 10, it is 34.34 amps. The integral of I squared, which represents the thermal stress on the overcurrent protection device, also varies over the first 10 cycles. Cycle 1 has 816.3, while cycles 1 through 10 has 1387.1. When selecting an overcurrent protection device, consider these inrush current characteristics. Firstly, the overcurrent protection device must be able to withstand the peak inrush current without tripping. Standard circuit breakers are designed to handle short-duration overcurrents. However, fuses may require special consideration. Secondly, the overcurrent protection device's time current curve should be coordinated with the transformer's thermal damage curve. This ensures that the device trips before the transformer is damaged by prolonged overcurrent. Thirdly, consider using a time delay or inverse time circuit breaker. These breakers allow short-duration overcurrents to pass without tripping, while still providing protection against sustained overloads. Fourthly, some applications may require the use of fuses specifically designed for transformer protection. These fuses have a high inrush current withstand capability and can provide better coordination with the transformer's thermal damage curve. The transformer is rated at 30 kV amperes with a primary voltage of 480 volts. We can calculate the full load current using the formula kV amperes divided by the voltage divided by the square root of 3. So 30 kV amperes, or 30,000 volt amps, divided by 480 volts, divided by the square root of 3, which is approximately 1.732, gives us a full load current of approximately 36.1 amps. The inrush current is significantly higher than the full load current. The peak inrush current of 460.66 amps is more than 12 times the full load current. This highlights the importance of considering inrush current when selecting overcurrent protection. Now let's consider the available data to select an appropriate overcurrent protection device. We need to choose a device that will not trip on the inrush current, but will still protect the transformer from sustained overloads. A standard circuit breaker with an inverse time characteristic may be suitable. The breaker's instantaneous trip setting should be above the peak inrush current of 460.66 amps. However, it should also be low enough to provide adequate short-circuit protection. The breaker's long time trip setting should be based on the transformer's full load current. A typical recommendation is to set the long time trip at 125% of the full load current. In this case, 125% of 36.1 amps is approximately 45.1 amps. Therefore, a 50 amp circuit breaker might be a suitable choice. However, it is important to verify that the breaker's time current curve is coordinated with the transformer's thermal damage curve. Alternatively, a time delay fuse could be used. Time delay fuses can withstand high inrush currents without opening. A fuse with a rating of 50 amps or 60 amps may be appropriate. Again, it is important to verify that the fuse's time current curve is coordinated with the transformer's thermal damage curve. To ensure proper coordination, consult the transformer manufacturer's recommendations and the overcurrent protection device manufacturer's data sheets. Additionally, conduct a coordination study to verify that the selected overcurrent protection device will protect the transformer and coordinate with other protective devices in the system. The integral of I² values provide information about the energy that the overcurrent protection device must be able to withstand during the inrush event. The higher the integral of I² value, the more energy the device must be able to absorb without failing. Overcurrent protection devices have an I²T rating, which indicates the amount of energy they can withstand. Ensure that the overcurrent protection device's I²T rating is higher than the expected integral of I² value during the inrush event. The data shows that the integral of I² reaches a maximum value of 1387.1 after 10 cycles. Select an overcurrent protection device with an I²T rating greater than this value. In summary, selecting the right overcurrent protection for a transformer requires a careful consideration of the inrush current characteristics, the transformer's full load current, and the coordination of the protective devices. Analyzing the peak and average inrush currents, as well as the integral of I² values, will help in making an informed decision. Always consult the manufacturer's recommendations and conduct a coordination study to ensure proper protection and coordination. The information provided is based on typical values and general guidelines. Specific applications may require additional considerations. For example, transformers with higher impedances may have lower inrush currents. Transformers operating at higher frequencies may have different inrush current characteristics. Also, the ambient temperature could affect the performance of overcurrent protection devices. High temperatures can reduce the device's current carrying capacity and lower its trip time. The NEC, or National Electrical Code, provides guidance on overcurrent protection for transformers. NEC Section 450.3 provides requirements for transformer overcurrent protection. The specific requirements depend on the transformer size, voltage, and application. Consult the NEC for detailed information. In addition to overcurrent protection, transformers also require ground fault protection. Ground fault protection detects and interrupts ground faults, which can cause significant damage to the transformer and create a safety hazard. Ground fault protection is typically provided by a ground fault relay and a dedicated ground fault circuit breaker. The ground fault relay monitors the current flowing in the grounding conductor. If the current exceeds a predetermined threshold, the relay trips the ground fault circuit breaker, isolating the transformer from the system. Proper grounding is essential for effective ground fault protection. The grounding system should be designed to provide a low impedance path for ground fault currents to flow back to the source. This ensures that the ground fault relay can quickly detect and interrupt ground faults. Regularly inspect and test the overcurrent protection and ground fault protection systems to ensure they are functioning properly. This includes testing the circuit breakers, fuses, and relays to verify that they trip at the correct current levels and within the specified time limits. Keep records of all inspections and tests. If any problems are found, take corrective action immediately. By understanding transformer inrush current and following these guidelines, you can select and coordinate overcurrent protection devices to protect your transformers from damage and ensure the safety of your electrical system. Proper transformer protection is crucial for maintaining the reliability and efficiency of electrical power distribution systems. Transformers are critical components in electrical power systems, and their protection is essential to ensure the reliable and safe operation of these systems. In addition to the factors already discussed, there are some other important considerations when selecting overcurrent protection for transformers. Firstly, consider the transformer's impedance. The transformer's impedance limits the fault current that can flow during a short circuit. Higher impedance transformers will have lower fault currents. The overcurrent protection device must be able to interrupt the maximum fault current that the transformer can deliver. Secondly, consider the transformer's loading. The transformer's loading affects its operating temperature. High-loaded transformers will operate at higher temperatures. The overcurrent protection device's ampacity must be directed for the operating temperature. Thirdly, consider the transformer's location. The transformer's location affects its exposure to environmental factors such as temperature, humidity, and corrosive atmospheres. The overcurrent protection device must be suitable for the environmental conditions. Fourthly, consider the type of load that the transformer serves. Different types of loads have different inrush current characteristics. For example, motor loads have high inrush currents when they are started. The overcurrent protection device must be able to withstand the inrush current of the load. Fifthly, consider the coordination with other protective devices in the system. The overcurrent protection device must be coordinated with other protective devices in the system to ensure that the fault is cleared by the device closest to the fault. This minimizes the impact of the fault on the system. Sixthly, consider the applicable codes and standards. The NEC and other codes and standards provide requirements for transformer overcurrent protection. The overcurrent protection device must comply with all applicable codes and standards. Seventhly, consider the manufacturer's recommendations. The transformer manufacturer and the overcurrent protection device manufacturer provide recommendations for transformer overcurrent protection. These recommendations should be followed. Selecting the right overcurrent protection for a transformer is a complex process that requires careful consideration of many factors. It is important to consult with a qualified electrical engineer to ensure that the overcurrent protection is properly selected and coordinated. In addition to the technical considerations, there are also some economic considerations. The cost of the overcurrent protection device should be balanced against the cost of potential damage to the transformer and the cost of downtime. A more expensive overcurrent protection device may provide better protection and reduce the risk of damage to the transformer. However, it may not be cost-effective in all applications. Finally, it is important to document the overcurrent protection design. The documentation should include the transformer's nameplate data, the overcurrent protection device's ratings, the coordination study, and the applicable codes and standards. The documentation should be kept in a safe place and should be readily available for future reference. In summary, selecting the right overcurrent protection for a transformer is a critical task that requires careful consideration of many factors. By following these guidelines and consulting with a qualified electrical engineer, you can ensure that your transformers are properly protected from damage and that your electrical system operates safely and reliably.